Hello, hello. How we doing today? Glad to hear it. So, we're continuing on our reinforcement learning kick, okay? And as we will have one more homework assignment before we finish the course, okay? Um, Likely having to do with reinforcement learning, given given such background to it, okay? And it makes sense from an overall perspective of the various types of machine learning. In fact, we kind of have these on the board right behind me. Like the major versions. We spent a lot of time unsupervised. Okay, reinforcement learning is a real useful paradigm of machine learning. Okay, and let's see, are we good here? Yeah, we're good. We're good. All right. Awesome. So we're gonna continue trying to code machine learning. Now, last week, a week ago, we did our coding lecture, and I was tickled to pieces over the fact that we did the silly frog problem. Okay, the silly frog problem is something I've been wanting to do for a long time. Where we did this very funny. Actually, let me pull up the silly frog. Actual. Here we go. There's our silly frog problem here. There we go. Yeah, we had our silly frog. It was it is very simple policy. The question is, does it try to jump to the left or jump to the right? And it's a silly frog, so it may or may not do what it needs to do. But it has these little discrete states, and you want to avoid these mean old alligators. Okay, what's the policy? And we coded from scratch just using Python and NumPy. Okay, we did dynamic programming to figure out what the optimal policy was to update the value function. And based upon the value function, it says, hey, when we're over here, try to jump to the right. When we're over here, try to jump to the left. And it figured it out, right? Okay, and that works for these and this was a very well suited problem for these value function related reinforcement learning approaches. We had a very simple reward. Don't go in here. Don't go in there. Anywhere else is gravy. Anywhere else is good. Okay, it's all fine. The frog is still alive, and the states were very discrete. So as a result, our value function could just be a list of states we could be in, any one of these states, right? And what is the value of them? Okay, literally just a table, a list. It doesn't get much simpler than that. Okay, now, however, in a lot of applications of machine learning, we don't have this nice discrete, like with these little countable states. Okay, sometimes, my friends, we have something like this. Okay, so this is a classic example of a lunar lander. This is the Gymnasium package within Python. It's free and available, and hopefully we get to play a little bit with this package today. But more or less, these are physical devices to be controlled with reinforcement learning. And this here is an environment. Okay, and in this environment, you might have a certain action space. Like, hey, I want to land this lunar lander, right? Actually, somewhat topical with these recent lunar missions that have been launching. They are not landing on the moon currently, but regardless, regardless, this is the states here are not fully these discrete states. This lander is not in position 2 meters, 1 meter, 0 meters. It could be any real value in between, right? So when you go back to our dear friend, our silly frog, okay, those have those discrete states. But in real life, if we're dealing with physical systems, they will have continuous states, okay? And so it's worth talking a little bit about the idea of states and what we would have to do to take the reinforcement learning that we would apply in this silly frog problem using maybe dynamic programming to something with these continuous states here, where our states have to be continuous and then they have to come up with some action at the end. All right. And that's going to take us to deep reinforcement learning, which we did cover at the end of the Tuesday lecture. We talked about actor critic methods. Okay. And so that's what we're going to build toward today. We'll see how far we get in the actual coding of it, but we have to cover a number of different concepts to really take us from where we were to where we want to be for coding up a reinforcement learning approach for these types of problems. So let me go back to here and let me change to a new Notepad set. So today is 2026 0409. Some deep reinforcement learning. DRL. Okay. Now, specifically, what we're going to be trying to apply this to are problems where we have continuous dynamics. Okay, but anyway, we'll talk a little bit about this in a couple of ways. There's lots of things we want to cover. One is the fact that we need to be able to simulate an environment. Okay, all right. We also need to be able to build an actor critic network. The actor is the thing that does the actions. It's like, hey, lunar lander, do this thing. Okay. The critic is what's evaluating, was that a good action? It's like, was that good? Was that bad? That's like the value function we've been talking about, right? Okay. We also want to talk about how we represent states and in actions. All right. And a few odds and ends, some details for practical implementation of DRL. Because right now we're getting to the point where it's not always so sometimes when I do these coding examples, I can just build it up from scratch and explain everything that's going into every step of it pretty clearly and sort of motivate why we made a particular choice as opposed to other choices. Well, sometimes in deep learning, you will just make choices that just seem to have to that like you just like, look, this is just helpful. Just do this. People have found that this is helpful for kind of X, Y, or Z reasons. Like one thing that's really important is normalizing. The data, okay? All right. And there are some things that are important, such as clipping. Sometimes people talk about clipping losses or clipping rewards. Really what that means is like if something gets too big, you kind of clip it off. It doesn't go much further, it doesn't go much bigger. Okay. Things like softmax or like are ways of sort of clipping values. These are just things that people just realize are important. Okay, so sometimes you have to show, hey, if we don't do this, it doesn't work so well, but if we do it, it does. Or you say, hey, look, people have found that, hey, when you normalize the data is well established, you got to do. Or clipping the data, people have shown it's useful. We just do it and we show that it works, right? Okay, things like that. All right. So let's talk a bit about some of these concepts. All right. One is sort of simulating this environment because it's so important within reinforcement learning that the idea is you have some agent, you have some environment, okay? The agent does an action, and then the environment sends back the state and the reward R, okay? Now, we talk about simulating an environment because if you're doing deep learning or any machine learning where there's a large enough network or just a lot of parameters, what do you need? You need a lot of data, right? A lot of data where of the agent trying something, doing an action, getting a state back. And in the era of modern computing, the easiest way to do this is by not using a real physical environment where things can go haywire and break. Use a computer simulation of the environment to see what happens. This is now a standard in all manner of reinforcement learning, is that if you have a physical system that you want to improve how it operates, by far the most popular approach is to come up with a simulation of that environment that's good enough that when you come up with a policy for this agent, you just put it on the real system and it works pretty well. okay? You transfer from a simulated environment to a real environment, right? And that's where different coding packages come into play. Now, if you are a mechanical engineer, which statistically 100% of my class is, right? You take entire courses on trying to come up with the physics, the equations that describe the physics of motion of physical systems. What be they mechanical systems, be they fluid systems. I'm teaching an advanced dynamics course in the fall. That's for mechanical systems. And it's all about coming up with equations of motion. Or if you're taking my applied optimal controls course, even just today, we just showed techniques for coming up with the equations of motion of these systems, right? For the machine learning purposes, for machine learning purposes, it's helpful if we just have those equations in some kind of environment. So conveniently enough, there are entire packages such as Gymnasium here. Okay, here's Gymnasium. You search Python Gymnasium. This is what comes up. All right. So here's that lunar lander example, right? But there's not the only example. You can go, it builds a whole bunch of environments for you. So that way you don't have to do that math for the physics, right? So if you look at classic control, you have a lot of examples. Oh, look, a pendulum here. Classic example of a pendulum. Probably sick of this if you're in my other class, okay? Where your job is, as an agent, is to apply a torque. You can see that little arrow going clickety click, 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 clicking around, right? Trying to balance the pendulum. So that's the action, is what is up. In fact, it tells you, hey, the action space is a floating point value, like a real number, between -2 and 2. That's the action space for this pendulum. This is built for you, so you don't have to. It says, hey, what's the observation space? Okay. And it'll tell you it's just a floating point number. Okay. Floating point number between what and what? It looks like it's between -1 and 1. Not sure what the third value is, but anyway, so it gives you, it'll explain to you. Okay. Observation space. All right. It'll give you the X value of the pendulum, the Y value of the pendulum, and the speed of the pendulum. Those are the three variables. That's the observation space. Those are the states. Okay. We're talking about states. What they call observations is the states. Okay. This is built for you if you want to use it. And in fact, they have code showing you, hey, you want to set up the Gymnasium? Here it is. Here's how you set it up. And this is all built in, so you can set it up with Google Colab. All right. But these environments, and so you can build your own environments. You're not only limited to these, and there are in fact tutorials for building your own environment from scratch using the physics engine that's provided here through this Python library. All right, let's do another example. So let's go to the control examples. It was for reinforcement learning and control. Let's go through the cart pole. Okay, this is what we want to get to. Maybe not by the end of today, but by the end of next lecture, we should have an implementation of the cart pole. All right. So, all right. And here on the cart pole, you'll see it says, oh, what is your action space? Discrete 2. 2 discrete actions. It can do 2 things. The action is you can push left on this cart, or you can push right on this cart. Right? So it has this environment all set up for you, right? And then the observation space are these 4 numbers, not 3 numbers. What are those 4 numbers? So these observations, those are states. Now recall, for our system to be Markov, we need to have enough states that completely represent what the system is gonna do. Okay, and so make sure what those states are. Well, we have 2 bodies on this cart, and so what you need are the position of the cart, the speed of the cart, the angle of the pendulum, and the angular speed of the pendulum. Those are the 4 states it's talking about. It gives you the range here. Okay, that's where it goes. So, and here's the action space. Look, 0, push cart to the left. 1, push cart to the right. Very simple. So basically, you're trying to jiggle this cart around so it stays up. That's the goal of the cart pole. All right. So the observation space, exactly what I was talking about. These are your states: the cart position, cart speed, velocity specifically, the pole angle, and the pole angular velocity. Okay, that's what those are. Okay, so these are all set up for you for these particular examples. But just a little bit about what you need to know. So So for simulating dynamical systems, these are systems that move, okay, where things change over time. In continuous time, you need to know the correct states, okay? So if you were given the equations of motion for some kind of system, let's do an example, okay? Let's say you have the cart pole minus the pole. This is just a cart, okay? And you apply a force to it, some force. That's your action, okay? It could be left or right, or it could be a continuous variable, a real number with floating point number between a certain range, whatever it is, right? If you wanted to know the correct states to include, so that way you know everything you need to know, so it's Markov, you have a full observation, okay? What you need are the equations of motion. Let's say that here is the position, we'll call the position, oh no, S is already taken, x of t, right? Well, if you were to get the equations of motion, you could do you're all mechanical engineers. You've done free body diagrams. You say the sum of the forces is equal to the mass times the acceleration. And the acceleration is going to be the second derivative, or as we call it, x double dot in the differential equations business. That's the second derivative with respect to time. Let me just rewrite that just because that's not necessarily commonly known, right? F equals ma, right? Therefore, the second derivative of x with respect to t dt is equal to the sum of your forces. Let's assume there's no friction on the cart. The only force on it is F, is equal to F, which can change over time, over m. Okay? So the quick hack to knowing how many states you need to know, what observations you need, okay, we'll call it your state vector. Here we'll call it S just because computer scientists decided to call it S for state. If you're a controls person, you would call it X probably. All right. Okay. What you need to know is that that you look at the order of your differential equation. It's a second order differential equation. That's a dt squared. Okay. Second, there's two derivatives. You need two states. And if you have two variables, each of which have two derivatives, then you have four states. If you have three variables, each of which have two derivatives, you have six states, etc. For most mechanical systems, for every degree of freedom, you add two states, and you need a position and a velocity. So you fill it up with all of the states from the lowest order derivative to the highest order derivative, dx dt, except the highest one. That's the quick hack to knowing what observations you need in a mechanical system. That's what they've done here. So if you have the cart pole, you've got some position x of t and some pole position theta of t, right? Then your state, you're going to need two states for each of these. So four in total. You'll need a position and a velocity of x and a position and velocity of theta. That's literally what they have in the example that we're seeing on my screen when I pull it back up. You have x dot, that's just dx dt, for those who don't know. And theta dot, that's d theta dt. That's the speed. Okay, that's for the cart pole. And if we go back to our screen, sure enough, that's what we see. Position, speed, position, speed. Okay? You can include more information than you need in reinforcement learning. That may or may not be helpful. It might make your state space bigger than it needs to be, so it might not be helpful, but it could be. It could theoretically be. right? So you need to know the correct number of states, all right? Then the idea of simulating a system the idea is that you have some current state S at time I, okay? Then over some small delta time, some small time step, delta time, and applying some action A, it becomes Si plus 1. Right? Second here. One up the thing. All right. So the idea is that something happens. Apologies. Screwing that up. Right? Is that you take an action. Over a small period of time, it changes your state from one state to the next. This is a state transition. So over the course of simulating an entire motion of some physical space, you're going to move from one state to the next, to the next, to the next, to the next, to the next. It's going to be moving over time. You can change your action over time. When you apply some action, it's going to change your it's going to change your state. So you might see, so the way to look at it might be, here's time, here's state. Let's just assume this is one of your states. You could have many states, right? For our card pole, we have 4 states. Let's just assume this is one of those. You got all these little time steps. We'll call those delta t. And it might move around in some kind of way based upon those actions, right? Those are states at each time step. Okay. All right. So now the environment's job is to do all that, do all those state transitions for you. Okay. So, and you can get this for all kinds of different things. Oh, there's lots of other fun environments. For those of you looking through the environment section of Gymnasium, check out MuJoCo down here. MuJoCo is a 3D simulation package. Let's go there. MuJoCo. And look, you have all of these different examples. You have a little robot arm that's trying to reach a target. You have a little walking, like kind of a cute little walking robot right here. A whole humanoid that's trying to get to stand up and do stuff. Oh, here's the half cheetah. It's on his back right there. Anyway, so this is a fully 3D simulation environment that you can use. Okay, that there are examples of. So feel free to check it out. So let's look at the humanoid stand up. Let's see if we can they actually have an example of it. Looks like it's just right now it's just flopping around on the ground. This is a pretty hard reinforcement learning problem to get it to flop up. But you can see, look at all of the different states of this humanoid. Okay, here's the action space. It's torques at how many different joints? Every one of these joints is a torque. That's the action space. And the observation space is you look at every single degree of freedom of this humanoid, and you have a position and speed for each, position and velocity specifically. Okay, so that's how these environments are set up and work. Okay, so that's the big picture of simulating an environment. And thankfully, a lot of these Python libraries have handled that for you already. Now, let's go back to our go back to our notes here. So you have a simulation environment that basically its job is to take in different actions and then it'll bop you around from state to state to state, okay? And those states can do things like inform your reward, right? For your reinforcement learning. What is the reward that you get? Okay. Right, next topic. So now this is where things are going to look pretty familiar to some of our prior work in building neural networks, deep neural networks. Here for here in our Canvas in our coding environment. Okay. We're going to be, so we could set up an actor critic network. Okay. So now the idea behind this idea that we were covering in last class is that if we set up an actor network and a critic network, this allows us to use gradient-based optimizers like stochastic gradient descent with momentum, or the atom optimizer, which is a fancier version of using momentum that we coded from scratch in class. Okay, we can use those methods to update our policy. Actor-critic network. So here we'll have our actor. Okay, and the actor is like the agent. It's the thing that's sending out actions. Goes to our environment, env, and out comes our state. Goes all the way back up to our actor. Right. But that state and our action go to our critic. Okay. So that state and also the reward come to the critic. What was the action that we sent? Okay. And we send back to the actor some kind of delta. That delta we called a temporal difference, or TD error. And more or less all it was saying, hey, friend, this actor, this thing that you did, is it better? Did it perform better or worse than we expected? So think of this critic network, think of that as the value function. And both of these things can be a deep neural network. This can be a deep neural network. Okay? So you can represent your actor, which is your policy, as a deep neural network, and your critic as a deep neural network. Two different deep neural networks. Okay? The only job of the critic is to be able to predict what the value is going to be of taking a certain action at a certain state. That's its only job. So this is that value function. This is a classic supervised learning problem. In is going to go some input, out is going to be some prediction of the value, which we're going to be able to assess, all right? But it's the actor that's going to be updating its neural network based upon maximizing the expected return, the reward, okay? Based upon its experience. So with that, we can actually start setting up what we're trying to get to, which is a cart pole environment. So what we're going to try to set up here is our cart pole with this information that we have. Okay, there's the cart pole in the gymnasium document. And all we need to do is import gymnasium into our google.colab collab.research.google.com. Okay, and it'll have access to all this stuff. Pretty great. It's never been easier. Okay, and it has already set up a lot of the basics of what you will need for reinforcement learning to get this cart pole to balance. okay? For instance, it already has an action space set up for you. If the action is 0, it pushes cart to the left. If the action is if it's 1, it pushes the cart to the right. So it's going to be trying to actively say, this is my current state, this is my position, this is my speeds. What should I do, right? Push left or right. Yep. Now, it also has in a built-in reward. And this is where we actually get into the engineering of the reinforcement learning problem, okay? Because who decides what the reward is? We do. We decide the reward. So this is the way that, let me just write out. This is the way that rewards are often computed for these problems, okay? Okay, so for simulated environments, we evaluate expected reward across an episode, quote unquote. An episode. What's an episode? Well, we can kind of see what an episode is. Let me go back to this. Watch this pendulum going back and forth real quick. Let's see if I can zoom in a little bit so it'll make it a little larger, okay? You'll notice that when it kind of leans a little bit too far to the side, the pendulum suddenly snaps back up to the top, okay? What happens is we've established a termination condition for this environment. When something bad enough happens, you stop, okay? And you give it a it's like that. Everything stops. You start over, okay? So, and when you terminate, that is the end of the episode. Okay, and so in the way in the way that this particular environment has a built-in termination condition is that when the pendulum leans a little bit too far to one side or the other, boom, it stops and then restarts. Okay, at which point the episode has ended. You are done calculating the reward for that episode. Okay, and the way that to create a reward that incentivizes staying upright, here's a really simple reward. How much time is the pendulum alive and active before it is terminated? Boom. Just count up the amount of time. The longer it stays up, the better, right? That's a very simple reward. The longer it stays up, the better. And longer in this case is literally just a number of time steps. We're calling here are our individual time steps. 1 time step, 2 time step, 3 time step, 4 time step. It's just saying it's doing a transition from one state to the next. And as long as it's doing state transitions and it has not hit this termination condition, boom, add up more reward, more. And that's exactly the way we have this set up by default. You can change the reward if you would like. It's totally reasonable. Say, here we go. This is the built-in reward. Since the goal is to keep the pole upright for as long as possible, by default, a reward of +1 is given for every step taken. By step, we mean time step. That's this right here, your little delta T. A little tiny time step, all right? Okay, including the termination step. The default reward threshold is 500, okay, or 200 for V0. Basically, they say at some point they stop, okay? After 500 time steps or 200 time steps, depending on the version, you're done. You can't do any better, right? We consider it succeeded, all right? And this is just, and this is a choice that people have found is really helpful for making reinforcement learning work in these environments, that you have a condition that says, you're done, stop. All the information after that is not very useful. So stop it, start it over, see if you can do better, right? And if you're done well enough, stop it. You're good enough, stop, right? Okay, all right. And there's another version of this, is the Sutton-Bartow reward, and this is very similar to my Silly Frog reward. Sutton-Bartow being the authors of the reinforcement learning textbook that I was showing off over the last few classes. All right, it's a reward of 0 for every non-terminating step and -1 for the terminating step. That was literally what we had for Silly Frog. That when it's on a safe lily pad, there's nothing bad happens. That's great. But if it hits the alligator, boom, dead, right? -1, bad reward. Okay. All right. And here, so another important element of these episodes is some degree of randomness. And this is normally encoded in the starting position of the cart pole. You don't start it in the exact same configuration every single time. You add a little bit of randomness. And so they draw a uniform random value between 0.05 and negative 0.05. That's what zero is approximately half a degree, I think. Wait a second. I think it's half a degree because 0.1 is 60 is so 1 radian is 60 degrees. This is 1/20th of it, so it's like 3 degrees. Yeah, about plus or minus 3 degrees, right? Okay, and here you go. Here's the episode end. This is the termination condition they're talking about. It terminates if the pole angle is greater plus or minus 12 degrees. Okay, if it goes a little too far, boom, right? All right, it'll also terminate if the cart goes too far to the left or right. That's what that's showing, okay? And a truncation just means chopping off, chopping off something. And if the episode length is greater than 500, it stops, right? Okay? All right, and it gives you a little bit of code to get things started, but that's the environment. But also it has, in addition, these rewards, okay? So with that, let's actually start coding up the basics of some of this method, okay? We'll try to get an actor critic method going, all right? Get up the proper code base here. Okay. Colab.research.google.com is where I'm going. Just like we've done for so many classes. Okay. Okay, I'm creating a new notebook. And I'm pulling it up in just a second. Let's just make sure this is refreshing. Just a normal Colab notebook, friend. Okay, indeed. I think it's working all right. Now let's pull it up. Okay, got a new notebook. So I'm going to call it Cart Pole Actor Critic. Okay. Cart Pole Actor Critic. Now we're going to start with the libraries that we need, okay? So we got a few libraries. Some of these are going to help us out in a couple of different ways, all right? Okay. We're going to just do an import OS. This might help us with dealing with any operating system related challenges. Don't think too much about it, okay? So let's import our libraries. And let's put our name on our paper while we're at it, okay? Let's put our name on our paper. Let's see. This is our Cart Pole Actor Critic by Christian Hubicki. We're at colab.research.google.com. Write it out for those who are new to the stream. In case we have any new viewers. New viewers, my friend. Let's do, right? We are at colab.research.google.com. We can run all this code on your own Google account for free. Here we go. Right, that's where we are at. Okay. Christian Hubicki and all my friends here. 2026 04 09, a common era. I want to give credit to Jacob Hackett, our TA, and Gymnasium for some of the example code that's helpful to put this together, okay? Okay, and what we're going to do is going to create deep neural network training to balance a cart pole. Okay, so let's import our libraries. Okay, all right. We're gonna import a new let's import a good old NumPy as MP, aliased as NP. All right. We're gonna need our neural networks, so we're gonna need Keras. So we're going to import. First, let's do some TensorFlow as TF to get some of this underlying neural network backpropagation capability all built in. Okay. Now let's import Keras. That's our much easier interface to all this as we're moving along. We'll import Keras, and from Keras, we're going to import ops, and these are operators. These are like important operators. These are like your soft maxes. These are your tan h's. These are all of those activation functions that we can get to. We can put them in as ops for operator. Okay, from Keras we import our operators, and from Keras let's import our layers, our ability to make all these neural network layers. All right. Okay, let's import our plotting libraries. Let's import matplotlib.pyplot aliased as PLT, as we often do. Okay, and let's see. All right, and we're also, since we're going to have a little cart poll, let's see if we animate that cart poll. So we're going to say from matplotlib, we're going to import the animation packages. Okay, so we can actually have some, you know, my silly frog, I loved it, but at the very end of the day, I was just looking at a vector that I knew was like, yes, that says jump left. Yes, that's some jump right. That's great, but it'd be great to animate this stuff. So this is all for animating the cart poll. What else do we need? Okay, and we can do some special display commands. So we're gonna follow this along from capital IPython dot display. We're going to import HTML, display, and the ability to clear our output. This is going to help us display in a really convenient way an animation that we can click a button and have it balance a pendulum. Okay, that's just helpful to have. I'll put that into the chat, and also let me share the link. So everyone in the meeting. Okay, let me quickly make a shareable link here so everyone can follow along. Okay, anyone with the link can view. Copy the link, please. All right, I'm gonna put that in the chat, and if someone could put that in the YouTube chat as well, that'd be helpful. Okay, that in the YouTube chat. All right, cool. Now, that's all well and good, but let's also import Gymnasium. This is what we're talking about. This is all this Gymnasium work as Gym. Okay, let's make sure that it's all import okay. Do they import okay? Did I screw anything up in the actual code here? And Jacob was extremely helpful making sure I got all the syntax right beforehand, so thank you to Jacob. All right. Make sure this is working before we move on any further. Okay, because once we have this working, what we're going to next do is make sure we have the environment included, and then we're going to start building our networks. Oh, look, it looks like it worked, or at least did not throw any errors, I will say. Okay, so let's make a new code block, all right? So let's establish our cart poll environment. Okay, the cart poll environment, one thing that's helpful is a random seed, or random number generation, RNG seed. That way we're all dealing with the same outcome. There's not just that any randomness that's involved in the outcome of this, which there will be, is all controlled. So we're getting the same random outcome, if that makes sense. It does make sense if you think about it. So we got to just give it a random seed, and we like to do 42, the life, the universe, anything and everything as a random seed. Okay. Now let's start do our cart poll environment. Let's also do our hyperparameters, our reinforcement learning hyperparameters. Now, hyperparameters, we remember those are things that are like our step sizes from our supervised learning methods. Here, it's things like discount factors, okay, from our Bellman equation. So those discount factors were things like a gamma. So let's do a gamma of 0.99. That's a value in between. So this is our discount factor. All right. Also, I didn't say reinforcement learning in the title here. Let's go up to, so reinforcement learning of a deep reinforcement learning, of a deep neural network training to balance a cart poll. All right. So to recall the Bellman equation, that's that gamma, okay, discount factor, okay? We also want to set our max steps per episode. We want to make sure that we don't run the simulation for an episode that's too long and just hangs and takes forever. It's good to set a maximum. And Jacob recommends 10,000. Jacob has been my guru for deep reinforcement learning. So I trust him, which is just a way of me passing the buck on to him. No, but I tried this. I tried this out, and it worked out great. So thank you, Jacob. All right. So now we have the environment. Okay, this is going to rely heavily on the gymnasium package, on the library, that the gymnasium. Okay, so we're going to create an environment. We'll call it env. Okay, we're going to say gym dot make, and we're going to make a very particular model. They have one already named, so it's going to be cart, capital C cart, capital P pole, hyphen v0. So it's capital POLE hyphen v0. Okay, there you go. We have, that's the environment. Okay, we can also give it a render mode for how it's actually going to look on screen. So we're going to say render underscore mode is equal to RGB array. So this is a mode of how it's going to look. Okay, so there's going to be some things that are not going to be hyper obvious, but if you want to go into the documentation, see what other options there are, you absolutely can. Okay, for a gymnasium. All right. Now, here's the other thing. We want to be able to set a reset command. So we want to reset it. Environment reset using a particular random seed. So this establishes how the environment is randomly reset upright, right? And that randomness is going to be set by this random seed. That's all just saying. That way we are all dealing with the exact same random resets when we are running our reinforcement learning problem. Okay? All right. All right, now we need to set the number of episodes. So eps. Okay. So we're gonna, let's just do some make sure we have some file information that's all working okay. np.finfo, so file information. Okay. np.float32.eps.item. Okay, item. I put this in the code. Let's make sure this all runs. This gives us the actual file location. Okay, for our episode info. Okay, so that's all stored in case we need it for later. Okay, so let's run that. Okay. All right. So now, we set up our environment. Cartpole environment, we have a random seed. We also have a discount factor we've already set up and max steps per episode. Okay. Now, let's go to actually setting up our critic network. Now, this will start to look like our neural networks, our feed-forward neural networks that we did in prior examples using Keras. It's going to look very similar, okay? So let's do that, okay? So let's set up the actor-critic network. Okay? And there are and for any neural network, let's go back to our screen up here, okay? So we've got, for some network, we're going to have a certain number of input layers, input units. Then we're going to have some hidden layer in the middle. Those are our hidden units. And you can have multiple layers multiple hidden layers. Guess what? We won't need multiple hidden layers to do what we need to do. You can add more if you want, but here we can actually get away with fewer. Okay? All right? And you have num actions. Okay, so sorry, you have your outputs, right? Those are your output units. Okay? So the number of inputs. So this thing, if this is going to represent, so we have two networks. We have two networks. Let's make this bigger for you all. I apologize. Okay. We're going to have two networks. One of which is going to be the actor network. The other is going to be the critic network. Okay. So they serve two different purposes. All right. So the actor network, its job is what we call the policy. Right? That means it's going to have a state that's going to come out as an action. So for the policy, okay, you're going to want to have come in 1, 2, 3, 4 states, right? We had 4 states, one of which was the position x, x dot, theta, theta dot. You had 4 states, and out pops an action. It's 0 or 1. There are 2 ways you could do this. You could have a single action that comes out, and it is blocked off as being between 0 and 1. And if it's closer to 0, you choose 0. If it's closer to 1, you could choose 1. Or you could have 2 outputs. One is for go left, one is for go right. And whichever is bigger is the one you do, right? There are multiple ways you could do that. So let's do it in the way where you have a single. So it's gated between 0 and 1. Okay? Or sorry, yeah. Let's do the opposite. Sorry. So you have where you have two values. So you have left and right. Whichever is bigger, you go in that direction. You can do a max. Which of those 2 is the bigger, right? Take the soft max of left and right. Whichever is the bigger one, you go with. Okay? That's your policy. Or we would call that pi. All right? Cool. All right. So that's your actor network, right? Now for your critic network, the idea is it takes in, again, all of your states, which is 4 states, x, x dot, theta, theta dot, and out comes a value. What's the value of that state? A single value, okay? So a single output. So it's got 4, so you got 4 inputs here. You got 4 inputs here. You're going to have 2 outputs for this. And you're going to have 1 output for your value, okay? And then we're going to do a single hidden layer neural network here. Okay, it turns out we won't need more than 1. You can add more, but one thing you'll find is that the more complicated, if you make your network more layers and complex than necessary, okay, it's going to take a lot more data to train. And unlike in prior examples where our data was just given a priori, like, oh, here's your data, it's in a list, right? Here we generate our own data by interactions with the environment, right? So every time you want a new data point as to how well this actor did, what do you got to do? You have to simulate this environment in a bunch of loops, okay? And that takes time. You have to generate all these time steps over and over and over again, right? Okay? Now, in modern times, we have ways of parallelizing many different simulations at the same time on GPUs. They're pretty darn good at parallelizing that sort of thing, okay? But one thing you cannot parallelize is the actual steps of going forward, okay? Because knowing how you get from that state to that state requires knowing how you got from that state to that state, and etc., right? It requires knowing that. A second here. So you can't parallelize that. That's what one requires knowing what happened previously, okay? So we now have 2 networks, each of which has 4 inputs, but one of which has 2 outputs and one is only 1 output. So let's put that together, okay? So let's go back to our code. So we're going to set up the actor critic network. Oops, I lost there we go. Set up so let's have num inputs. Number of inputs we set up is 4, right? That's x. That's the time derivative of x dx. That's theta. And the time derivative of theta d theta. Right? The number of actions, you can either go left or right, and we're just going to take whichever one is the maximum of those two. So you have 2 actions, right? So we will choose either left or right, depending on which is bigger. Okay? And then you have your actor. Sorry, you have your num hidden layers. So num hidden layers, hidden units. So and we'll just do 256. Powers of 2 are a good place to start. So we'll go with that. This is the number of neurons in our single hidden layer. You can have multiple hidden layers, no worries, okay? But you might not need it. At least we've shown that when playing around with this ourselves, we don't need it, okay? All right, so now let's set up our actor network. That's our policy. Right, that's our state in, action out, right? So what are our actor inputs? So let's use the layers object. This is part of the Keras packaging. So Keras layers, what is our input and the shape of that input? Okay, shape equals, open parenthesis, num inputs, comma, okay? This is all this is saying is that our inputs are a 4x1 vector, okay? We have four inputs. Again, the 2 positions and 2 velocities of the cart, okay? And that as layers with a plural S, as it's reminding me here. Layers with an S. Okay, layers, there we go. Let's make sure, yeah, this is all running so far. Okay, all right, now let's do actor hidden layers. Hidden layer, singular, okay? Let's add a layer. Layers, make it a dense layer so everything is connected to everything else, fully connected, okay? Open parenthesis, num hidden, okay? Now let's give it an activation function, okay? Now a very common activation function for reinforcement learning is the swish function. Let me. I'm losing all my pens on the ground right now. Okay, activation is equal a swish. Oh, swish, SWISH within quotes. Okay, got a swish. Okay, and what are the inputs? The inputs are the critic. Sorry, are the actor inputs. Apologies, lost my place. All right. Now the swish function, we have not talked much about the swish function. Let me pull that up. Swish function looks kind of like this. Here you have X, and then you have the swish of X. It kind of looks like, it's like a line here and sort of like a, let me get the curve right. Okay, like that. So it's a little bit like a ReLU. Remember, a ReLU looks like this, where it's flat and it becomes linear, right? A rectified linear unit, that's a ReLU. This is like a smoothed out, very differentiable, smooth swish function. Now, the actual math for it is it's a sigmoid, which sigmoid is, it looks like this, you know, where it kind of activates and comes flat, and you multiply it by X. It looks like this. So it's so swish is X over 1 plus e to the minus beta times X, where beta is roughly the sharpness. The bigger the beta, the sharper it is. Okay. So anyway, that's the swish function. So we'll have the swish activation input for our code. Now we need our output layer, right? Output layer, actor output is equal to layers dot dense. That's another dense layer. We love our dense layers. Okay. And on that layer, we want the number of actions, which again, in this case is 2. And we're going to do an activation, which is a softmax, okay? Which says what the maximum of these 2, all right? Softmax. So it tells us the maximum of those 2 things. Whichever is bigger, that's the direction we go, okay? And this is our act, and what goes in is the actor hidden layer. Okay, that's the input to that layer. So that's how they connect up, right? So the hidden layer its input is the input layer, the output layer, the input is the hidden layer. Okay. Let's make sure this is all running so far. Good, running, no issues. All right, now let's do the critic network. The critic is a separate network. Critic network, okay? Think of that as the value function estimator. Okay, it tells us how useful it is to be in a certain state. Okay, if you also had the action in there, it would technically be a Q function. Anyway, whatever, but that's a, don't want to get too bogged down in the details today. All right, so let's do the same thing. Let's do the critic inputs. Critic inputs underscore. Okay, so layers dot input. It's going to be the exact same shape as the other one because it still has all the states as its inputs. Its shape is equal to num inputs, comma. Excuse me. All right. Cool. Neat. All right. Now we have our critic hidden layer. Very similar. Where the layers dot, you want to make a dense layer that connects up, num hidden. And our activation, we'll use the swish activation as well. Okay, that's the activation function, turning it on. But the input into it, of course, are the critic inputs, right? Critic inputs. Okay. That gets us to our output layer. So it's a critic output. Okay. It's going to be a dense layer. Okay. But all it's going to be is a dense layer, but it only has one output, right? That's the value, the scalar value. What is the value? It's like the reward accumulator of time. It's not a vector, just one number. That's our output, right? And the input into that is the critic hidden layer. We don't need any activation on that. All we need to say is like, hey, sum up all the other previous layers together. That's going to give us a number, okay? And that's going to tell us what our value is. All right, critic hidden layer, layers, again, layers with an S. Okay. Yep. And this code is adapted from official Keras examples, you know, to be clear, and Keras examples, in addition, using the Gymnasium library as well. I just want to make that clear. That's where this is all adapted from. We will include the links to, if we can just put the links that we just put in the Zoom chat on the YouTube chat as well for various examples you can follow along as to how this is put together. Okay, you can find additional examples there that you can go off of. All right, okay, we're still moving forward. So we have these layers. Okay, let's put them all together in a model. Okay, so let's here do a model. We'll make a Keras dot capital model open parenthesis. Okay. And our inputs to this overall model are our actor inputs and our critic inputs, comma, and our outputs for this overall model are our actor outputs and our critic output singular. Actor output, critic output. Okay, so this makes a Keras model. If you want to make sure you put it together right, you can always say model.summary. Open, close. What did I screw up here? Critic inputs layer.input shape. Keras.layers input, maybe not inputs, input. I don't need an S there. Okay, and extra S for inputs. And here you go. There's our model summary. So we can see what our model looks like. Okay, so you have these input layers, which are vectors with four each. Okay, then you have these dense layers with a certain number of parameters that all are fully connected there. Okay, makes sense. You have 4 inputs times 256. That's going to give you 1280. Okay, so connections, and then out to our 2 outputs for the actor network. So it's going to be 256 times 2. That's 514. It includes the biases, right? It includes the biases. That's why it's in there as well. And then just an output to 257. That's what there's a bias that goes out to the final layer for the value function estimation without an activation. Okay, great. Look, here we have a Keras neural network. Again, building up the layers, using object-oriented programming, saying, here's your input, here's your hidden layer, here's your output, right? Okay. All right, now here's we get to the kind of the tricky bit, okay, with the training. And there's a couple of things, there's a lot of components that are gonna have to go into the training, and we're probably gonna have to stop very shortly and finish this up next week, given the time that we have. We're gonna have the training loop, okay? Because we're gonna need to train this model. That means we're gonna need a few things, okay? When we're doing any machine learning model, what are the 4 things you need, friends? What are the 4 things you need? You need data. Well, the data we're gonna get from simulating our actor interacting with our environment and getting reward. That's how we're gonna get our data out, right? So we're gonna need that simulation, okay? We also are gonna need a cost function, a model, and we have a model. Guess what? We put together, this is our whole model. That's nice. We have data, we got our model. What are the 2 other things? The other 2 other components of machine learning. We need an optimizer. We're going to use the Adam optimizer, just like we've used for a lot of these Keras examples. It's just a smart stochastic gradient descent. It's helpful. What's the last thing that we need? The cost function or the loss function, okay? Now, the critic network has an easier loss function. It could be just a mean squared error. We're really literally just trying to take examples of value as we measure them and try to get the network to predict those, right? That's supervised learning. That's a classic one. It's mean squared error, okay? Instead, we're going to use something called the Huber loss function. It's nice. You know, people playing around with this have found this to be a nice loss function. It's just a modified version of the mean squared error, which we'll get to. But it's the same concept. It's just the worse your prediction that's bad, make them line up better, okay? All right. And for our actor, that's where we're going to want to be maximizing return. Okay, so like the negative of our reward. You want a high reward, so you want to minimize negative reward. Okay, right? So that's, and there's going to be some additional layers on top of that. Okay, but let's get started here. So we have our training loop. So let's talk about some of these losses. So we need an optimizer. Okay. Now, thankfully, Keras has already have so many built-in optimizers for us. It makes this pretty simple, okay? So we're going to grab from the list of Keras optimizers, keras.optimizers.atom. Open, close, and we have to assign a learning rate. So let's set a learning rate, and just by thumb in the wind, we'll do a 1,000th, so 0.001. Slow learning rate, just to make sure we find a policy, okay? All right, so that's our optimizer. That's pretty simple, right? One of our 4 key components of machine learning or optimizer. Hey, let's use Adam. Done. All right. So now for our loss function, our cost function, specifically for our critic, that's our mean squared error loss. We're calling the Huber loss. So HUBR Huber underscore loss equal to Keras.losses.Huber. Open close parenthesis to grab that as a function. Now, what is the Huber loss? Let's pull it up here. The Huber loss, let's compare it with the mean squared error loss, okay? Okay. So losses, so error-based loss. Okay. So if you have error on this axis, okay, and loss on this axis, the mean squared error more or less going to look like this. It's a squared error, right? MSE. Makes sense, right? That's a parabola acting on your error. Now the Huber loss looks a lot like the parabola until you hit a certain point, then it just starts behaving linearly, okay? That way the loss doesn't become too crazy too fast, okay? There's more to it than that, but that's like a really dumbed down basic version of it, right? So it's going to be, I'm gonna draw it in blue right here. It's the Huber loss is a quadratic, but at some point, draw that a little bit differently. Just it is a quadratic, right? But at some point it breaks away and just becomes linear. The Huber loss, Huber. Okay. So think about how much of machine learning is like just happily crafting these nifty little curves that happen to be nice when you put them together with machine learning. That's the Huber loss. Okay, and that's what we need for our supervised method, which is what the critic method does, right? We just want to fit the value function. That's the only thing we want to do with that. Okay. We have a Huber loss, okay? Let's say this is a modified, don't need that. A modified mean squared error for the critic network. Okay. All right. All right. So now we need to start setting up our environment in order to sum up our rewards. Okay. So all right. So we're going to create a history of actions and a history of critic values. Okay. We're basically be able to take over the course of a whole episode. We want to remember what has happened in a given episode, so that way we can inform the reward functions and the loss functions for these networks. Okay, we're running a little. Oh, we're almost out of time entirely. Okay, this is actually perfect time to stop, I think. So when we next move on, okay, we're gonna get into the nitty gritty of taking everything that we're getting here. Okay, we've set up, and then getting the reward function set up with the discount factor, so that we have our losses. And once we set up our losses, we can do our training. Okay, with the environment. That's what we'll start up with next time. Okay. All right. Thank you all very much. I hope you have learned. I hope you're really, we're actually, I'd say about 2/3 done. 2/3 is done, maybe over half done for a deep reinforcement learning example. Thanks to all these wonderful packages, these examples. Again, thank you from the Keras library. Thank you from the Gymnasium library. That will make this so much simpler to actually accomplish within the space of one lecture period. So again, thank you all very much for coming. I really appreciate it. Have a great day. Have a great weekend, and talk soon.